First, we consider a situation that there is an dielectric interface between air and a high-index substrate. And as we know, for the plane dielectric interface, the reflection coefficient is defined as Z sub 02 minus Z sub 01 over Z sub 02 plus Z sub 01. Due to the large difference between Z sub 02 and Z sub 01, we will have a very high reflection. But in some application, we may want to the light can be total incident into the substrate. In this session, we would like to use quarter wave dielectric layer to reduce the reflection at the dielectric interface. And consider the situation as plotted in this figure. We have a substrate here with the material index mu0 and epsilon. And of course, the material properties of the air is mu0 and epsilon 0. Between the air and the substrate, we place a dielectric layer of thickness d. The properties of this dielectric is mu0 and epsilon 1. An incident wave propagates with angle theta 0 with respect to the normal vector to the interface. And we will have the transmitted wave in the dielectric layer with the propagation angle theta 1 with respect to the normal vector. And in substrate, the light will propagate with angle theta with respect to the normal vector as shown in this plot. According to these angles, we can define the characteristic impedance in each layer. In air region, the characteristic is Z sub 0, which is eta 0 over cosine theta 0. And in the dielectric layer, due to the propagating angle is theta 1, we can have the characteristic impedance is Z01, which is eta 1 over cosine theta 1. As in the substrate, the corresponding characteristic impedance is defined as Z of 0, which is eta over cosine theta. Okay, and we define the coordinate for this interface is Z is 0. Due to the thickness of the layer is d, so we can say that the coordinate for this interface is Z equals to minus d. Okay, and at this interface, we know that a little bit below this interface, we can have the wave impedance is Z of 0, which is the characteristic impedance for the substrate. And due to this dielectric layer, we can transform this wave impedance to this position, and we define it as capital Z of minus d. Let me plot it a little bit lower. And above this interface, it will be the characteristic impedance of Z0. Okay, between these two materials, we will have the corresponding reflection coefficient gamma of minus d. And of course, you can find out the value of gamma of minus d by these two parameters. And in this session, our purpose is that to reduce the reflection at this interface. So our goal is to let gamma of minus d to be 0. As we can achieve this situation, then this means that the reflection will be 0. Okay? And as I have mentioned, the function of this dielectric layer is that it can transform the wave impedance from Z of 0 to Z of minus D. And if we can let Z of minus D to be Z sub 0, which is equal to this value, then across this interface there will be no reflection. Okay? And we have also known that Z of 0, the value of Z of 0 is like this. And the value of Z sub 0 is the characteristic impedance of air, and it is this one. And clearly you can see that the Z sub 0 is a real number, so to have these two to be equal to each other, the Z of minus D should be also a real number. So to transfer a real number wave impedance to another real number of wave impedance, we will use the quarter wave dielectric layer. So we let Z of minus D to be minus quarter lambda Z. Please keep in mind that the quarter wavelength means the wavelength in dielectric layer here over 4. Okay, the lambda Z here means the wavelength in this material, not the wavelength in air or in a substrate. Okay, this is very important. If we let the thickness of the dielectric layer to be this one, then we will know that we can easily obtain the wave impedance transformation to be Z of minus D is Z01 square over Z of 0. Okay, this result can be obtained in previous session. If you have forgot it, please go to the previous session to check for this one. Take the value of Z01 and Z of 01 into this equation, then it can be expressed as this one. And you can see that this term stands for Z01 square, and this term represents the inverse of Z of 0. Okay, so by use the quarter wave dielectric layer for material 1, we can transform the impedance from Z of 0 to Z of minus D, and the value of Z minus D is expressed here. After we have known the value of Z of minus D, then let's see how to reduce how to make the reflection to be 0. We have said that if we can let Z of minus d to be equal to z 0. Then we will make the reflection coefficient at minus d to be 0, right? This is our purpose. And in previous slide, we have learned that by the quarter wave dielectric layer, the z of minus d can be obtained as this one. And the value of z sub 0 is this one. So you can see that to satisfy this condition, you will have n1 square times cosine theta 1 square is equal to n times cosine theta times cosine theta 0. Okay? So if you can satisfy this equation, then you will have the reflection at this position to be 0. And of course, we consider the very simple case when the theta 0, the incident angle is 0 degree. As the incident angle is 0, then we will have theta 1 equals to theta equals to 0 degree. And all the cosine here should be 1. Then the condition will be simplified as n1 square equals to n, or you can just say n1 is square root of n. So this one is the condition that for normal incidence, if you want to have no reflection, you can put a quarter wave dielectric layer over a substrate, and the index of the dielectric layer should be square root of n, which is the substrate index. Okay? Besides, please note that this condition is only for normal instance, for the incident angle is 0. But the reflection will be increased with respect to the incident angle. This means that the reflection is function of theta. So this condition is only designed for one theta value. To have satisfied the no reflection for other theta value, you have to derive other conditions. Okay. And the quarter wave dielectric layer is frequently used in solar cell. As we know, the function of the solar cell is that the light can come into the solar cell to transform the light into the electric and Hall pair. And due to the high index difference between the solar cell substrate and the air, we will have very high reflection. Then it will reduce the amount of light into the solar cell. So we would like to put a dielectric layer over the solar cell to reduce the reflection. Then we can have more incident light into the solar cell. Such kind of the dielectric layer, we call it anti-reflection coating. Anti means no or against. Okay, so anti-reflection coating, which is also called ARC, is used to reduce the reflection. And this figure plot the reflection of one layer anti-reflection coating with different thickness. As you can see, at this specified thickness of the dielectric layer, you will have very relatively small reflection. Okay, and this thickness just is corresponds to the quarter wavelength thickness. And for such kind of ARC, we have only put one layer. We call it one layer ARC. And in your research, if you want to reduce the reflection, you can choose one layer ARC over the substrate or over your device to reduce the reflection and have more light into your material.